Okay, I'm talking about Xen PV drivers today. My interest in PV drivers comes from the fact that I'm a maintainer of the Xen-related kernel coding in Linux. So I have to deal a lot with PV drivers, and I want to tell you a little bit why do we want them. What are PV drivers and how do they work? So why do we want PV drivers and what are PV drivers? PV stands for Paravirtualized. PV devices are software-defined devices which are usable as a replacement for real devices and virtual machines like disks, network devices, display drivers, whatever else. They are working usually at a higher protocol level as real devices. For example, the PV disks are working at the block layer instead of having to program a PCI SCSI controller to take the SCSI control blocks, and then those SCSI control blocks may be dependent on the disk device, and I have to block the I have to program the DMA controller or whatever else. So PV drivers are much simpler in this regard. They are used to route I/O requests from a virtual machine or a guest to the host, which is capable of controlling the physical devices. So a PV device is always in a layer above the physical device, where the physical device is driven by the host and the virtual device is driven by the guest. The main motivation why we want to use PV drivers is emulation of real hardware. It's a complicated thing. If you ever look into QEMU, what it's doing to, let's say, do a block I/O, it's rather complicated, very many software layers involved, and you have to trap a lot of guest accesses. So this results in emulation being much slower than transferring a logical I/O request to the host. Another advantage of PV drivers is when you're emulating an existing physical device and now a new device is coming into scene which has some new nice shiny feature. For example, it can handle more I/Os concurrently or things like that. Usually you would have to add an emulation for this new device to be able to use it, and you would need the driver for this device and the guest. Adding new features to a PV driver or PV device is much easier because it's purely software defined, and you don't have to add a completely new emulation of the physical device, but you can just add a new flag and then use the driver for the new device and host. Okay, so now that we know that PV devices are a nice thing for virtualization, I want to talk a little bit about Xen architecture before going into detail with the PV drivers. Xen architecture is rather simple. You have a hypervisor, a type 1 hypervisor, which is rather small compared to the kernel, for example. Having nearly no native drivers inside, only those which are needed to boot the hypervisor and operate it. But the main I/O and the main device drivers are all in .0. So I have in .0 all the device drivers. .0 can access the physical devices, and in the guest domains Those can be HVM domains, fully hardware virtualized domains, for example, Windows, or PV domains, which are much faster, but don't have legacy stuff inside. In .0, I have the backends of the PV drivers. I have XenStore, that's a basic Xen piece of architecture. And for HVM devices, I have normally a GNU process emulating the legacy hardware. I can modify Xen a little bit by putting all the backends in dedicated domains, putting XenStore in a dedicated domain. Even it's possible to put the GNU process in a dedicated domain, a so-called subdomain. And this is one of the main advantages of Xen, that it's possible to disaggregate Xen and reduce single points of failures this way. All the following I'm telling about PV drivers theoretically work in this environment as well as in the standard configuration where everything is in .0. One example for disaggregated Xen architecture is, for example, Cubes, which is using dedicated backend domains. And in SLE 15 at SUSE, we will use a dedicated XenStore domain. So, when we compare, for example, block.io, bare metal versus Xen, what's different? On bare metal, I have a user program doing file I/O, which will go to the file system, to the block layer, to the hardware-dependent driver, SCSI, IDE, whatever, which will call the specific PCI card driver, which will go physically to the bus, to the disk. In Xen, it's a little bit different. I have in a user domain, user program doing I/O, file system, block layer, that's the same. But then I'm not going to the SCSI or IDE driver, but to the block front driver, which will talk via the hypervisor to the block back driver .0, which then sits above the block layer again, which then can use the SCSI driver, PCI card driver, as on the bare metal case, which will then go out to the physical disk. When you would, in case you would do complete emulation of the physical device, you would have, laser is visible here, the emulation below the PCI card driver. So there would be complete emulation level, a layer going then to the block layer, SCSI driver, PCI card driver, and so on. So here I'm skipping the SCSI IDE driver and PCI card driver layer in the W. Okay, what types of PV drivers are there? The most common ones are the disk driver, block interface, using the block interface, the network PV driver, working on the IP level. There are PV console driver, PV frame buffer driver, so console is the text console. Frame buffer, of course, is the graphics. There are PV SCSI drivers, which could be used as the replacement for the disk driver, but there are some disadvantages because live migration with SCSI PV driver is very complicated. And there's PV USB. Rather new PV sound, Paravirtualized multi-touch driver, Paravirtualized display drivers. Those three are in development by Global Logic and EPAM. and there's a streams driver working on the streams level. There are different backend architectures possible. The most common ones are the kernel backends, for example, blockback, netback, SCSIback. Those are the most performant ones, of course. There are QEMU-based backends. There is existing a disk backend based on QEMU. There's frame buffer and USB. There's a zero daemon based backend drivers, for example, console. Okay, now that was the more general part. Now we're coming to the Xen infrastructure, which is used to realize PV drivers. So there are different mechanisms used in Xen for the PV driver. One of the most important are grants. Grants are a way to share memory pages between guests. So this way, a guest can give a memory page, for example, to the .0, so it can do I/O for the guest. A guest which wants to grant access another domain will set up the grant interface with a hypervisor at boot time, resulting in an array of grant entries in memory. When it is running, it doesn't need to call into the hypervisor any longer for granting pages to another guest or .0. This is very important for performance, of course. So when granting access to a page, it just fills a grant entry in the memory page which was negotiated with the hypervisor. It fills an entry with a PSM and the domain ID it wants to grant access to, and gives the access rights of the other side, so you can't grant a page read-only, for example. And that's all it needs to do. On the other side, for example, .0, the guest wanting to access a granted page needs to issue a hypercall to map a grant, because it has to add this foreign page into its own page tables, which is normally not allowed, of course, because this would be a security breach. So it specifies the domain ID of the granting domain and the index to the guest's grant entry array. Of course, it has to know the index somehow. This will come later. And with this hypercall, it's possible to map the foreign page or multiple foreign pages into its own memory. When it's done with using that grant, it issues another hypercall to unmap the page again. So, a little bit visualized. The .0 at first creates a grant table entry, just putting the entry to its grant table. The grant table is known by the hypervisor. It passes the grant reference to .0. .0 will then issue a hypercall to map the grant, which will lead to the hypervisor verifying the reference and mapping the page into .0. And what the hypervisor is doing, it is incrementing the use counter in the grant table so that the guest knows that the grant is in use. So, for example, when a page is used 5 times, it will have the index 5 there, and when the guest is done with I/O at the end, it can verify that the use counter is 0 before freeing the memory page again. so that there's no memory corruption. Another basic mechanism are event channels. It's more or less a paravirtualized interrupt mechanism. Paravirtualized, again, in the sense that the guest is aware that it's using a virtualized resource. That's the basic meaning of paravirtualized. It's something virtualized, but the guest is aware of the fact that it's virtualized. Event channels are used for inter-domain signaling, not only, but this is the usage for paravirtualized devices. And each event channel between two domains works both ways. So .u can interrupt .0 and .0 can interrupt .u via the same event channel. The guest is able to select the basic mechanism, either a bitmap-based event channel, where up to 4096 event channels are possible for 64-bit domains, or the more modern one is a FIFO queue, which can serve more than 100,000 event channels per domain. Sending an event is done via hypercall, again, and the receiving domain does that either via an IRQ of an emulating send device. This is a virtual device defined by Xen. Or the faster method is the guest can register a callback, which is directly activated by the hypervisor in case an event is coming in. On the Xen architecture slide, we have already seen XenStore. XenStore is a store for configuration details, accessible by all guests, built similarly to a file system, so it's a hierarchical name-value store with access rights, so the owner of an entry can specify which other guests are allowed to read or write an entry. In order not to be able to flood XenStore, it's possible to set quota for guests so that the guest is limited in the amount of data it can occupy in XenStore or the number of entries it can create. It is possible to register watches so that any time an entry is modified, a guest which has registered a watch on that entry will receive a signal in the form of an event via event channel when items are being modified, added, or removed. XenStore supports transactions, so it's possible to modify multiple entries in an atomic way. So you can start a transaction, read some entries, modify the other entries or the same entries depending on the contents of the RAM entries, and at the end finish the transaction, and this will either succeed, so all modifications will be done at once, or it will fail, for example, in case one of the entries which you've read during the transaction has been modified in between by another guest. XenStore lives either in .0, that's the default, inside a daemon, or in a dedicated XenStore domain. Communication with XenStore is done by a shared memory ring, which is granted again, and event channels for the watches, for example. So this is an example of XenStore. You have multiple entries. What has to be noted that it is possible that a node having children can hold values as well. So it's like if you could write to a directory in the file system some contents other than other file entries. This, for example, are some of the entries which are used to configure a virtual network device. You have entries in domain 0 related to the backend VIF virtual IP function, and you have related entries in the front end side, so the guest, where you can see some state duplicated or some other information which are used by both sides. So the communication between front-end and back-end is done by memory pages owned by the front-end, and the front-end domain accesses grant to the back-end domain. So the back-end can access the memory pages, but when the front-end dies, the pages will go away. Normally, PD drivers, front-end and back-end, use a common layout in form of a ring buffer of fixed-sized slots used for requests and responses. Each request issued, for example, from front-end to back-end needs a response. I will come to that later. The same memory page has a header area with producer and consumer indices of requests and responses, where the producer is always greater or equal to the consumer. So when the producer is greater than the consumer, for example, for a request, then there's an outstanding request. And when the backend looks at the indices, it can see, oh, there's a request pending for me. Normally, the front-end is producer of requests and consumer of responses, and the back-end, of course, the other way around. But there are examples where it's the other way around. For example, PV-USB driver uses for the normal IOs such a normal ring, and for hot plug events, when when a USB device is plugged in virtually for the guest, it's just the other way around. The backend will have a request to the front end telling it that there's a new device. So this is how it works. The front end will produce requests which the backend is consuming. In the same page, the responses, sorry. The responses produced by the backend are consumed then by the front end. So this makes it clear why that each request must be followed by a response, because otherwise the requests would try to overtake the responses, and this would lead to memory clutter. So after putting a new request into the ring, the front-end signals the back-end via event channel that there's a new request pending. The other way around, when the back-end is putting a new response into the ring, it signals the front-end that there's a response pending now. It could happen, of course, that the ring is full, so the front-end has put as many requests as possible to the ring page, and there's no free room anymore. When the backend is seeing that and it consumes a request, making place for a new request, it will signal the front end that there's new space available in case it wants to put a new request in there. So how are PV devices configured and initialized? Configuration of PV devices is the job of the Xen tools. They normally read the Xen guest configuration and write appropriate Xen store entries regarding the PV devices into Xen store. Those are the backend and the front-end entries we've seen before. The backend then receives a Xen store watch event because a new entry for this backend has been written and waits for the front end to connect. I will come to that later how this happens. When a domain is booted and the front end driver is initialized, it scans Xen store entries in order to detect any entries which were present from the beginning. Or it receives Xen store entries in case a device is hot plugged into the configuration when the domain is already running. When the front end detects a new device, it will connect to the backend. And then front end and backend will negotiate device parameters via Xen store in the initialization sequence. So, in an example, I've a disk config file. I have a file-backed disk, so this is just a large file on the backend side, and the front end sees that as a block device. When the Xen tools read the config file, they will produce the following entries for the backend. So local domain 0, backend, VBD, virtual block device. The 1 is the domain ID of the guest. The 768 is a little bit cryptical device number. And it, for example, writes the front-end parameter, it's local domain 1 device VBD 768. You can see down there, local domain 1 device VBD 768 is the related front-end path. You see that the local file is in parents. You can have a script which is called at device creation on the backend side. Your front-end ID, you have the online, so the disk is really there. It could be offline theoretically. You have a removable parameter, for example, for CDs, for emulated CD-ROMs. A bootable flag state. This is very important for connecting between front-end and backend. State is 1 in the beginning. The name of the device on front-end side, HDA. And some other parameters. It's writable, it's a disk, and at end. On the front-end side, you have the Xen store path of the backend. You have the backend domain ID 0, so it's living in .0. It could be a driver domain theoretically, and state is initially 1 as well. So backend and frontend have the state node in Xen store readable by the other side. So the state 1 needs initializing. And then the next state is init wait, initialized, and then connected. Each of those steps have their semantics. Normally, initializing is the initial state. Init wait means that parameters are being negotiated between front-end and back-end. Initialized is that device features are being negotiated and connected. IOs can be performed. So when the backend has seen that the entries have been written, it will switch its state to init wait. So it's waiting for the front end to do further steps. The front end sees the back end has switched to init wait, so it has detected the configuration and it's waiting for the front end to write the parameters for communication. The main parts are the ring ref, that's the grant ID of the page used for the requests and responses, and the event channel for communication. In this case, it's possible to have multiple request-response queues, so the front end tells the back end it is capable to drive 2 queues. And of course, it needs the grant ID and the event channel for both queues. It's telling the protocol it wants to talk via the ring, and it can have another feature persistent in this case, meaning that some grants may be persistent grants, so they are not released after each I/O. The backend will see that the state has been switched to initialized after the frontend has written all those entries, reads those entries, establish the communication path, so granting the ring pages, connecting to the event channels, and then it will write the device features the guest can make use of. So, for example, feature persistent equals 1 is being written, so the guest can really use this feature, and it can use other device features as well. For example, for this block device, it can discard IOs or whatever else. And then it will set the state to 4, so connected. The front end reads the device features and then switches its state to 4 as well, and then IOs can happen. So now that the device has been initialized, the guest domain can start IOs. How do those work? So again, the picture we've seen before, the user program, a file IO, via file system, block layer to block front driver. Now we know how the block front driver will communicate with the block back driver, which will then do the IO. So in detail, the IO initiation. The IO started by the user in the WU, and finally reaches the front-end driver. The block front driver will put the new request into the ring page. It will put grant table entries into the grant table for the I/O data, and fill the request slot with all needed data in the ring page. Then it will increment the request producer index, so the new request is visible from this moment on by the backend. And to be sure the backend takes the request up, the event is sent to the backend that the new request is pending. At the backend, the event is received and finally routed to the blockback driver. The blockback driver will look into the ring page and find a new request. It will copy the complete request from the ring page into its own memory. This is very important because the blockback driver has to make sure that once it has read the request, it isn't being modified by the guest anymore, because of course the blockback driver has to verify the request, and if the verification is done and then the request will be modified afterwards, this will be a security breach. When the request has been copied, the consumer index and the root page can be incremented, so there's room for another request then. Next is that the blockback driver will map the granted pages into the backend domain. So the backend domain can then access that data of the guest. And finally, the I/O is started locally by the blockback driver to the physical device, or maybe to the file-backed I/O or whatever else. Preferred directly with the mapped grant pages, so don't directly DMA into the mapped grant pages, so modifying user memory at once. If this isn't possible, the blockback driver will use bounce buffers, so do the I/O to local buffers, and then after finishing the I/O, copying the data into the guest memory. So I/O completion at the backend, it's just the other way around. I've spared just reversing all the errors of the graphics and reversing the sequence of numbers. It's more or less just the other way around. The backend completion function is being activated by the low-level driver. The backend allocates a response slot on the ring page, fills the response slot with the I/O completion data, unmaps the grant pages, increments the response producer index, and then sends the event to the front end that the response is available in the ring page. And then we have the I/O completion on the front end. The event is received by the front end and routed to the front end driver. The front end driver looks into the ring page and finds the new response, takes the response data, revokes the branch via old data, of course looking whether the use counters are 0 or not. Increments the response consumer index, so making place for new responses in the ring, and calls the I/O completion function of the caller, and the I/O is done. So we have some possible optimizations in the complete process. One thing I've mentioned before is we can avoid, so the mapping costs are not, on front end we can't spare much time or much performance, but on the backend side we can avoid the mapping and unmapping costs by using persistent grants, for example, for data which is allocated by the front end and then used by the backend multiple times for each I/O request. You can have the same data page over and over again. So the front end can say this page is granted persistently, so the front end won't have to map unmap it over and over again, but it can leave it mapped. It is possible to avoid sending events in all cases. For example, when adding a request or response to the root page, when already another request or response was pending. So if I put a request on the ring page and put another request in there, and see that that the consumer index for requests hasn't been incremented, then I know that the backend will work on it eventually. So I can spare sending another event and let the backend consume 2 requests one after the other. This, of course, requires that the backend will cooperate and consume requests as long as there are outstanding requests, not only one request per event. And then, of course, it's possible to use multiple rings, as seen for the disk case, for example, to reflect parallel infrastructure like multi-queue, block.io, or if I have a network interface capable of performing parallel IOs, for example, Gigabit Ethernet normally has this capability. So that was PV devices. Yeah, I think I have been in time. Are there any questions?
Yeah, I have a question. To how PV USB, there are some old realization for PV USB stack, maybe 2009 or something like that. It was obsolete, but still working. And you mentioned, and I don't know if there are some new realization for PV USB stack, but mostly for QEMU only. Is there any plans for PV, just pure PV realization?
That doesn't rely completely on QEMU here, so you refer to here, this more or less. It is possible to build backends in other daemons, in Observer, for example, or
but as I assume USB now rely on QEMU implementation, not on pure kernel implementation.
So QEMU is the choice, has been the choice here for the backends, because for HVM domains you have a QEMU process already using all the infrastructure Xen has to offer here. So the QDIS backend, I think, was the first one here, or the frame buffer backend, whatever else, being integrated in QEMU. USB, for example, has been added later to QEMU. It was just added to QEMU because QEMU was already there. It would have been possible to use another daemon or use another special OS in a special domain or whatever. So it's not QEMU specific, but it's...
Yeah, I mean, but now it's implemented on this QEMU based backend. And I saw on ZenWiki that there are some plans for at least some basic implementation for just PV guests, PV backend.
Yeah, sure. So for example, there's a central piece in Xen tools to look whether QEMU has to be started for PV guests, because there are PV backends needed for the guests. This would have been to expand it either to start a special process for the guest, or you would have to start a daemon serving all the guests, for example, like it's done for the text console.